Hi, I'm Will.
I'm Gavin.
And we're here today to talk to you about our crazy invention, the holographic projector called the Voxiebox.
Thanks for coming.
Yeah, it's exciting to see such interest, and yeah, we want to keep things fairly informal. If you've got any questions at any stage, or just want to shout out something, then just go for it, and we'll have a chat about it. But yeah, we're keeping it fairly casual, and yeah. So it all started about 6 years ago. Gavin and I used to have a Thursday night lab session, which involved hanging out in my shed, drinking beer. And we came up with all sorts of crazy ideas, and the crazier the better. None of them made any sense. We had just finished working on an audio synthesizer that was controlled by a webcam that was pointing down at a white background surface. And then we'd gone out into the garden and caught a heap of ants, and we had the ants running around on the actual background there, and we're controlling what the synthesizer, the music the synthesizer made with by tracking the movement of the ants.
But it didn't sound very good because the ants just decided not to move around at all. They just sat around.
And the other good one we did was we had this great idea to use really strong magnets to connect to replace the bike clips on your shoes. So we duct taped the magnets to the bottom of our shoes and ready to get on the bike. I walked out of the shed. In the corner of my shed, the doorway of my shed, there's a metal rail. I never stepped on that. So that was the sort of calibre of crazy inventions that we're coming up with while drinking beer. Until one night we had a conversation that sort of, I said, well, what are we going to make next? And Gav said,
well, why don't we make a robot with a holographic projector for a head?
But that's impossible. Holographic projectors don't exist yet.
And I said, okay, so let's make one.
So we're totally joking, and we'd had a few beers, but we started playing around with laser pointers and started wagging a piece of cardboard back and forth in front of a laser pointer, and that made a line, like you get when you swing a stick around from a campfire or a glow stick or something like that. And so we thought, hang on a second, well, if we can actually make this sort of appear to float in midair, what if we actually chopped it up into individual...
if you could turn the spark off and on,
yeah,
then you could draw smaller segments and smaller segments, and maybe you could join the dots together to make things that actually appeared to float in midair. So
we got a Dremel, a high-speed drill, and put a disc on it that had slots cut out of it, and we attached that to the laser pointer with duct tape and shone at the wavy cardboard, and it produced these individual little points of light that were just floating in space. So we thought, oh, that's so crazy, it might just work.
So we've got this one floating point of light, it's like a little spark, and we thought if we could fill a volume full of these little sparks and we could turn them on and off like a room full of automatic, like little fireflies that you could control. If you could arrange them to go to a certain place at a certain time, then you could make a shape.
And then if we could do that, we could get
the... Okay, so this is what we decided we wanted to make. Okay, we didn't set the bar too high. Okay, we thought, yeah, Star Wars. Let's make something like Dejarik came from Star Wars. That was our target of what we could do. But obviously we thought there's no way we're going to do this, but it'll be a fun experiment, if you like. And one of the key drivers for us was we wanted to learn new skills, and we've been doing skills which are very much around machining, metalwork, making things, and we wanted to learn more about connecting computers together with hardware and controlling things and turning things on and off. And we thought it'd be a good fun project, and we just thought, let's just see where we can go and see where we get. So we decided we want to make a display with these parameters, something that would be a true three-dimensional volume of voxels. A voxel being a volumetric pixel, so it's not a flat square, it's a cube, much like you're probably familiar with Minecraft or that kind of idea. Lots of little building blocks. It had to be viewable from any angle. So we didn't want this idea that you could all stand in one direction looking at something. We wanted to be able to walk around this device and look at it, get your own perspective of it, and look down from above or from the side, whichever direction you chose. And we also didn't want a device that used 3D glasses, because we wanted to make something which we could use in all sorts of different spaces, not in someone's home or in a predefined kind of workshop. We wanted something that could sit in a public space, in an arcade or somewhere where people could just walk up and experience this kind of floating 3D effect.
One of the things about existing 3D TV displays is that what you're seeing is essentially a view of a 3D model. So you're not actually looking at the model itself. And that is illustrated by this slide up here, where you've got three people looking at a 3D object through the window, but they're all looking at it from a different angle, but seeing the same perspective. So this is one of the big limitations of existing 3D displays, that it really doesn't it's a simulation of 3D. It's really 2.5D.
Yeah, and the whole terminology, the whole scene, when you go to Google and you Google holographic display or volumetric display or 3D display, you'll see a completely diverse selection of images, and it's a really interesting experiment to do. You'll see things that are effectively illusionary, things with mirrors reflecting, you may have seen glass pyramids reflecting two-dimensional views of things. You'll see smoke screens, the two-pack hologram, that kind of thing. It's like live hologram.
So, I mean, that's actually probably worth pausing and having a think about, because you say, what people have done holograms and stuff like that. Well, those, it's based on a concept called Pepper's Ghost, and the way it works is you've actually got a two-dimensional screen, and it works really well for a room like this where everyone's sort of looking in the same direction, but it's only a two-dimensional screen, and it just appears to float there. So,
yeah, so there's a whole different way of talking about what's a hologram, what's not a hologram. Is that, as a holographic, when you look at what's just a genuine holographic plate, like that have been around for years, they are actually like a 3D screen. They're a view of something. Someone's chosen the perspective that you're going to look at. You can't walk around behind a hologram and look at it from the back. And we had a bit of a battle with ourselves in what we would call our display. We chose holographic display because the term holographic, in people's minds, it conjures up something, which is what the display looks like. We would have chosen a 3D display, but unfortunately the term 3D has been stolen by TV companies or whatever to effectively describe what's a stereographic display. So it's kind of like holographic in people's minds tends to be something that they have a very particular view of, and that's what we try to create. So,
and every now and then we always get someone who comes up and says, well, that's technically not a hologram. Well,
and we say technically you can look at it from more directions than a hologram, and then they kind of go, oh, well, yeah, okay. So what makes a holographic display different from a 2D display? So you buy a new monitor for your computer, and you look at the specifications on it, it's going to give you a resolution for your Z and your X-axis. Sorry, your Y and your X-axis. But we're introducing this new concept of the Z-axis. So we decided, we had a mindset on something we wanted to create, and we thought, how are we going to go about it?
So at this point we've been using just a laser, a single, cheap laser pointer laser, and waggling cardboard back and forth with spinny things. And we started to think, well, what we need to do, if we can get, rather than just a single point of light, a single beam of light, if we could use some sort of a screen. So with that in mind, we got this old Nokia phone and taped it to the head of my grandfather's old lawnmower and stuck a drill on the crankshaft and turned the phone on, fired it up and down. We've got this tiny little smoky cube of light. And that was a bit of a groundbreaking moment because it really looked, with all the lights off, it looked like, wow, this didn't actually have any, there wasn't actually any structure to it. We couldn't actually project any patterns with it.
It was a single voxel. It was one voxel. It was a cube.
But it still looked really cool. We got quite excited. So we started playing around with projectors, and we realised that one of the things that we needed was a high frame rate because for a normal 2D screen, you get in the 60 frames a second or 120 frames a second, whatever you get. But we had to fill that frame for however many vertical slices that we wanted to do. So we started hacking around with projectors. Sorry, I've gone off topic. One of the limitations here was that actually physically moving something up and down was really hard. Not only was it difficult to do accurately, it also the path that the screen would take would be a sine wave, so it would be slowing right down at the top and then going faster in the middle. We thought this would be a big problem, that all the models that we created would be totally stretched out in the middle and squashed up at the top.
So we decided to take a different track, and we started making helixes. We got obsessed with helixes, and it turns out they're really difficult to make. So what the idea was, if we could make, effectively, sometimes you see a truck going past and it's got these big augers on the back for drilling post holes. And if you take one section of that, one 360-degree revolution, and you spin it really quickly, you get a plane of a projection surface that's moving constantly in one direction. And we thought, if we can project onto this spinning surface a cross-sectional part of an object, and we can, in real time, make our computer create helical cross-sections, then if we could project those helical cross-sections onto the spinning shape at exactly the right speed, then we can perhaps draw out some kind of holographic shape, like an MRI scan done helically and projected onto this thing. So we spent a lot of time trying to make helixes. We made them out of ladies' tights and aluminium rods. We built a CNC machine ourselves in the shed, and we built these wooden ones. We made vacuum formed ones. We waited till Will's wife went out to the shop, so we used her oven to melt plastic when she wasn't there. And yeah, it was a lot of fun. And eventually we made...
when we first came up with the idea of using a helix rather than a flat surface, it was about 11:30 at night, and we'd had quite a few beers. And so we were looking around the house for something we could actually carve into a helix. And all we could find was a sweet potato. So we put the sweet potato on the lathe and made it nice and cylindrical, and then we sat there with a knife carving it out, and then we got the vacuum forming machine that we'd made and just vacuum formed the sweet potato. A couple of weeks later we found the sweet potato.
No, this is the wooden one. Sorry, this is the wooden one. This is the wooden one we made. Sorry,
there's the sweet potato. So go back to the other wooden one.
Yeah, okay, if I go back to the...
So that was a nice one that we made on a CNC machine, and we ended up vacuum forming a piece of styrene over that, and used that for a long time. We don't need to look at that anymore.
Okay. And then what we figured was, we had a laser pointer. We'd been messing around with this laser pointer, but what we needed was some... rather than delivering one dot of light at a time, we wanted to deliver a whole plane of light, because we wanted to create a cross-section of a scene, not just a single voxel. So we started messing around with DLP video projectors, because we knew that the Texas Instruments DLP chip was capable of producing many frames per second. And we'd taken apart, we bought like 5 of these are old in-focus projectors. We bought 5 of these on eBay for $150. And we thought, I know, what we'll do is we'll shine a laser. We'll take the bulb out. In fact, there was no bulb in it because that's why they were so cheap. We'll fire our laser through the projector and we'll create a cross-section of pure laser light. And the reason we thought we'd do that was because lasers don't have a problem with depth of focus. And because we were trying to focus onto a screen which was moving, we thought using a laser would be just brilliant because we would be able to, have it in focus at any time. So we decided to try and put a laser through a projector, which turned out to be more difficult than you'd imagine, because projector manufacturers in their wisdom are much like inkjet printer manufacturers. They put circuitry in there to stop you from using your own bulbs, because the bulbs they sell are like super expensive and they don't want you putting an LED bulb in a projector. But we thought, with our soldering iron, we can just bypass the electronic circuitry that stops the projector from working. But we didn't really have any knowledge of electronics. But it didn't stop us from experimenting.
We found these massive ceramic resistors, and we thought we'll just plug that into the projection, the bulb socket. And so we did that and flipped on the switch with our finger, and it worked for about 20 seconds, and then the resistor glowed white hot and caught fire and melted a hole all the way through the projector. So,
but we had 4 projectors left.
We had 4 more left. So we tried it again. This time we took the resistor out of the projector and put a massive heatsink on it and a fan and everything, and it worked for about 30 seconds before it caught fire. And this time it didn't burn a hole through the projector because we'd learnt.
So we'd learned that by using a resistor where the bulb goes, the projector's electronics kind of got confused and thought, there is a bulb there, I'll turn on the electronics. So we thought we needed a massive water-cooled resistor, something that wasn't going to burn out. So we were having a cup of tea thinking, where can we buy a massive water-cooled resistor? And then it was a eureka moment when we saw the kettle, and we thought, that's a massive water-cooled resistor.
So we plugged the kettle into the projector and fired it up, and it worked perfectly for about an hour, and then it made us a cup of tea. So that was fantastic. By that stage, we figured out that also there was about 15,000 volts going through that
kettle.
Little those wires that we had exposed there, so we turned it on with a stick there.
Yeah, but we got it working, and we wrote some software using processing.
Yep.
If you're familiar with the processing framework, it's a Java-based framework. We taught ourselves that. Will's a Java programmer by trade, and he taught me how to program in Java in a little bit, and we just submersed ourselves in processing, and we got to grips with the idea of generating 3D models in 3D Studio Max, various other things, using various scripts to slice them up like a meat slicer into lots of planes. So we were taking that data and we were sending it to the projector. We'd done some stuff with the color wheel to try and get more frames per second, and we started experimenting. And this is our first experiment. This is the results of our first holographic experiment. This is a little green elephant that we created.
So his head's kind of cut off there because it's on the wrong side of the helix coming through. But it was a real eureka moment. Like, oh my god, we've actually made something that's cool. You can sort of see that the electrical tape that's holding that whole thing together. And it's very back together, but it worked. And
we had this. So this thing was spinning, and it was being controlled by an electric motor with a pulse width modulator speed controller. So we had no control between the synchronization from the computer that was generating the slices and the speed of this motor. So we had this little volume control, which we had to spin this thing up, and then you kind of got to the point where the elephant would just drift off the top, and its head would go out and its legs come in the bottom, just like those old, if you're old enough to remember TVs when they had the vertical shift problem and you had to kind of get it just right.
And then it would stay there for like 5-10 seconds, and then it'd start drifting again. We had no idea why.
And one thing I didn't show here because it was too embarrassing is the first time we did this, we did wear bras on our heads like in Weird Science. This is the same set of tests we did. This was a collection of skulls that we made. Again, on spinning around 20 times a second. This is our first attempt at a chess set. And this is a little tiny solar system with a little Saturn over there. And those of you who remember Ghostbusters might remember, this one was animated. We had these little slimers flying around the shed. And we had a lot of fun because after a few beers, we had these little guys flying around, and Will discovered if you turned the laser pointer on and shone at them, you saw the laser beam going in and you could shoot the little ghosts, but they didn't interact. And here's another little Slimer, and then, we did some little T-Rex dinosaurs. And then one day we'd been kind of so absorbed by making stuff in the shed that we hadn't really been, we hadn't even thought about the concept that somebody else might have, because we'd never seen this display, we never thought for a moment that somebody else in the world might actually be making one too. And we saw this photograph on the internet. And we kind of shit our pants a little bit because we thought we were the only people in the world that were doing this.
So it turns out that there was this group of guys over in the US who'd been through the TechStars accelerator program, and they were working with big companies like Microsoft, and they were saying that they were going to launch a commercial product in the near future, and it was really exciting for them and stuff like that. And we were absolutely devastated. We thought, oh no, we'd worked. By this stage, we'd spent 3 or 4 years just hacking away in our sheds doing this thing, and it had never been something that we'd really invested ourselves fully into until it occurred to us, hang on a second, we're going to get beaten to market with this thing, and we better get a move on. So we had this mad scramble where all of a sudden we launched this crowdfunding campaign through Possible, and we didn't ask for much, we only asked $25,000 to bootstrap our project and get this thing going, and we made it. We launched a funding campaign before then, and it failed miserably, which was fantastic because we couldn't have delivered. There was no way we would be able to deliver that. Now we know that retrospectively. So
these were the guys in America who had made the Mastodon demo that we saw on YouTube. They called themselves Voxon, and they're comprised of 3 guys. The guy on the left, Sean Keane, he wrote a book called Meet the Connect about 3D data capture. He's the founder of the New York Volumetric Society. The guy on the far right is Alan Jackson, who's an engineer. He's been responsible for building several volumetric displays for museums in New York since the late 1980s. He made all sorts of different contraptions. And the guy in the middle, you may not recognize, but his name's Ken Silverman, and he wrote the graphics engine that powered Duke Nukem when he was 18 years old in his bedroom. So Ken was effectively the guy that launched, or he kind of almost single-handedly invented the modern day, what you call the modern day first-person shooter genre. Him and actually John Carmack was 3 years before him with Doom, and then Ken did the build engine which powered Duke Nukem and Blood and Ken's Labyrinth, and 3 years after Doom came out, this new engine revolutionized it, kind of blew away Doom engine because it could do things that sound ridiculous today about sloping floors, reflections in mirrors, and the fact that you could actually look around the place, not just stare straight ahead. So yeah, Ken was, he was this guy that we thought, great, let's get hold of him, and he's now our chief computer scientist. He's our chief computer scientist now, so that's been a real win. So yeah, these guys contacted us. We thought, this is amazing. They emailed us and said,
Hey, you guys have solved a heap of the technical problems we haven't figured out yet. We've got all these business structures and stuff like that, and let's join forces. So from being in a mad rush to beat these bastards to market, and how dare they come along and say they're going to do something, to all of a sudden, we just formed a company with them. So, so we've joined forces with them, and it's just been absolutely epic since then. That was about 18 months ago now, I reckon.
yeah.
And since we joined forces with them, the momentum, the amount of stuff that we've done has been absolutely, phenomenal. Just the energy that's gone into it. So while during the day here, while we're working away like mad at it, they're all sleeping. But while we sleep, they're working on the problems that we didn't quite finish yet. So it's just been this. It has been a mad scramble of just.
And when you're trying to carve out a niche in an entirely new market that doesn't exist already, one of the key things we all were very keen to avoid was another Betamax, VHS, or Blu-ray versus HDD format war. It's something that's brand new. Let's all get together and actually make something that we can all try and work at together. And we wanted to make it accessible, and we wanted to just, let's just share our hard work. So we got together with these guys, and we made our first ever. This is our first arcade unit, which
doesn't really look like much, but that's it. When it's turned on, you can see a little leap motion up in there, and arcade controls, and a little display at the top. So that was still a very early prototype, and we took it to the Maker Faire, and they gave us a prize. So that was pretty exciting.
But that was all running on our Java. That was running on our Java thing. So whilst somebody was trying to play chess with leap motion, someone was behind the scenes turning this volume knob to stop the chess pieces drifting out into space, so to speak.
So we were fully aware that Java wasn't the language to be doing something like this in, but it was my bread and butter. It was what I did during the day. And
what the things with Java is that when you're trying to build a graphics engine, when we go back to the number of frames per second, we need to create a holographic sort of image. When you're playing your video games on the 2D screen, 60 frames per second is the kind of the minimum you want for smooth motion. When you start extrapolating those slices out into three-dimensional space, we need to get up to about 3,000 frames per second. So that's what we're kind of shooting at with the system we're trying to make. It's a lot more, and not only that many frames per second, but the frames have to arrive at the screen timing-wise at exactly the right moment. Unlike if you're watching a movie at 24 frames per second movie, and you drop a frame, you're not really going to notice. But if you drop a slice on a moving display, suddenly everything gets a bit funny. So Ken Silverman, when he came on board at this point with his massively in-depth knowledge of computer graphics, and specifically the CPU, in which he's an absolute legendary programmer of, he knows it religiously inside and out. Probably one of the greatest minds in understanding how to get performance out of a CPU, and that was important. So he wrote us something which we call the Voxiebox DLL, and that is our volumetric graphics engine.
And it's remarkably efficient. It's so small. It's only
about a megabyte.
About a megabyte, and it's all self-modifying machine code and really low level stuff, and it's optimizes. Yeah. One of the interesting things is that with existing graphics engines, a lot of the processing power goes into that sort of post-rendering stuff, all the shaders and everything like that. You've got to do all this back surface culling and all this stuff like that. But all we need to do is get a 3D model absolutely raw and just spit that out. So all of that complex processing that has been the advancement of computer graphics over the last decade or two, we don't need to do that. We just need to get the raw data out to the projector.
So the DLL runs on a Intel, or whatever you call it, Wintel setup, 64-bit or 32-bit. It effectively handles the volume of, it's a volume buffer, if you like, in between the calling program and the actual Voxiebox prototype unit. So you can send it a bunch of commands, and based on a setting, we can either send it to a simulator. So we've got the option of running exactly the same graphics kernel and rendering a virtual Voxiebox to the screen and being able to rotate it and look at it. And what that allows is developers to code something and run it and test it. If it looks fine on the Voxiebox simulator, then when we bring in the real hardware, we just simply change a one-line setting and suddenly it's sending out to the real Voxiebox. So if we look at the kind of things that the DLL can do, these are the functions that it supports. So writing in C or C# or Java, you can just take some game code. You could write a game from scratch to create a voxel or a cube or a line or
And to
whatever.
date, most of our games have just been created from scratch. We've really only just started scratching the surface with the Unity stuff, but we'll get to that later.
Yeah. So we've got a bunch of these functions, and if we switch to these are some early photographs of the device running. So this is when our device was about 10 centimeters by 10 centimeters by only about 2 centimeters deep. So you can see this is one of our early depth map tests, and what really became really apparent was we could take a simple image, which was a color image with a grayscale image next to it, which represents the height, and we could start to see mountains, and we could start to see bathymetry, the ocean floor, the trenches. And when we took it out, people just started seeing data in a completely different way, and people would gather around it, and they would start to say, "Oh wow, I can see this," but someone else would be, "Look, if you come around here, you can see this. You know, look at the Himalayan plateau. It's really, really massive. I thought it was just Mount Everest." You know, people started to see data in a completely different way and unlock kind of ideas that they'd not previously seen. You can see this shot here. This is you can start to see when we started experimenting with color, how you get these slices. So this early prototype, you can see the slices quite apparently there, and some rippling stuff.
These ones were all done by a variation of the core graphics engine we call GraphCalc, which you type in a mathematical function to it and it calls it. That's an STL file, I think, that's used in 3D printing and various other CAD environments. But yeah, just as another application of medical imaging that you can do with it or something like that.
So we started experimenting with all these different uses, and it was apparent that there was so many different uses for the Voxiebox. From 3D visualization of medical. People always wanted us to do medical stuff, and it's a difficult thing because hospitals are very particular about the way they do things. Doctors like X-rays, and people imagine that they would much prefer to have a hologram of a skeleton, but in actual fact, it's not the case. We don't think at the moment. We also wrote simulator. So the simulator here is on the right and the Voxiebox on the left. So they look pretty similar. They give you the ability to see exactly what's going to happen when your code finally runs on the real hardware. And we experimented with depth cameras. This is Will's dad, Pete, getting his face scanned in 3D.
So that's using the Intel, at the time that they called that the Perspective camera. I think they've rebranded it and significantly improved the technology and called it the RealSense camera. And we've got one of their prototypes over in the US, and it's amazing. It's really exciting what's coming out in that sort of 3D depth sensing field. So we can use it to do holographic video conferencing, which is kind of cool. The whole "Help me Obi-Wan, you're my only hope." Yeah, we can do that. It's cool.
So yeah, these are just lots of little shots of various things, different types of media we experimented, from 3D models to games, terrain, Pac-Man, Formula 1 cars, bicycles, people. Really, we got so bogged down in, what can do.
Actually making the technology, but we didn't actually think, well, how are we actually going to use this?
Yeah.
I think ultimately the big potential application for this will be gaming. I think it just creates that we'll go into this more later, but that sort of shared social experience that is lost in a lot of today's games. But apart from that,
we just flick over and show the simulator just now.
Okay, yeah.
What we've got here is so this is our simulator.
Oh, no, it's not. Hang on.
How do you get to go to that one?
I don't know. There
we go. Can I use the keys here? Up and down. Might have to go off. Can we shut this down here so I can?
Sorry, guys. Something weird's happening there.
Just close everything in so I can see the desktop. Am I in presentation mode or something? Okay, so what I'm doing here is showing the simulator on screen. And the same code that you're seeing here is what runs on the real Voxiebox. So if I just bring up our little menu here, and I'll go down to this one here. Well, step through a few of the use cases. I've got it running in green mode just now, but we just support color as well. But what this particular model here emphasizes something that's very unique to the Voxiebox, and that is this idea that we call, well, this particular one, I've come up with a name because we like to invent new names when you invent a new product. This is perspective-specific encryption. And what that is this idea that you can create a model that looks different from different angles for different people at the same time. So this word here, if we rotate it around, and if I just move the mouse a little bit, it's quite hard to position exactly. It says hologram from one side. And if I spin it around the other side, it says Voxiebox. So that's a 3D STL file. And I created that by creating 8 little cubes, and then created the letters for each word, and in 3D Studio Max used a Boolean operation to subtract letters from different directions at the same time. So you create a physical object which looks different depending on the way you look at it. And whilst that's just a kind of a neat little trick, you can spin it around and you can see that it looks completely unrecognizable from a different direction. It actually unlocks what we call a unique gameplay opportunity for holographic gaming, and that is the idea that you could actually create a digital space where you have data that sits in that space that's only visible from a person from a specific point of view. So if you had a game of battleships or something where you had a head-up display, you could take someone's score or secret words or whatever, and you could use a grayscale displacement map and displace all the voxels in that image in a direction that's completely perpendicular to the person's point of view. So that text gets distorted, but they can see it, but anyone else in that playing space can only see this point cloud of data. So you start to understand this concept of a volume of space as opposed to a view of a space. It's a real view. So if we step through some of the other images in here, I'm just going to put it into color mode here. Bring up my menu, and you can see what color looks like on the Voxiebox. What we're doing is with the projection system, we're limited to because we're using so many frames per second, we're limited back to a color palette of primary red, green, and blue, which is a little bit like the ZX Spectrum from 1984, if anyone remembers that. In fact, we can mix those together to create the secondary cyan, magenta, and yellow as well. So it's a really interesting way. We're starting to go back to using Floyd Steinberg dithering to get color. When everyone else has got squillions of colors, we've got these kind of funky looking things, but they're holographic and they're 3D, and you can look at them from any direction. So we don't really care too much about that. There's a My Little Pony. I'm going to go down here. This is, I'll just switch back to monochrome mode because it looks better for this one. This is a model of the Dragon 1 spaceship. We did a demo last week, or guys in America did a demo last week to SpaceX, the space exploration company, to show how we could use the Voxiebox for visualizing CAD files. And I just downloaded this off Thingiverse, I think it was, and showed it to them, and they were like, "Whoa, where'd you get that from?" They thought that was cool. This is an interesting one. I don't know if you guys recognize this, but this is MC Escher's Flight of Stairs. And you can actually kind of just about get it to line up. So it looks like an illusion, but when you walk around the Voxiebox, you'll see it's just a funny shape. Anyway, that's the International Space Station. That's another one of those funny things. This one you probably recognize. It's X-Wing. You can zoom in and see the little guy inside it. Whoa. And we can also do animations. I'll bring up some animation. This is my first attempt at animating using DAZ Studio, which is a brilliant piece of software. This is a little animation I did called George and the Dragon, and he goes up and he kind of gives it a kiss, and then it was completely accidental. I was using the reason that the dragon looks so stupid is because he's actually being animated using Midnight Move sexy dances of a woman, because I couldn't find any dragon animation files. So he's actually doing a sexy dance, and the other guy, the little soldier guy, is also using the same, that's the disco, and he falls off the edge, right? So that's that. This is another perspective-specific encryption thing we did, which is a play on the what's the AMP advert from a few years ago. So it was taking the text file and morphing it in 3D space. It's a lunar lander, Millennium Falcon, oh, going away. Yeah, so again, you can see this one for the boys or whatever. You can start to see that the opportunity here to create data in 3D space, not just for fun, but we had a person who was into dancing say, that's really cool because I could plan dance choreography and I can look at it from a different direction. So they can look down on the Voxiebox physically from above and see the relationship between, the physical relationship between the different people. So you can turn it and you can zoom it and you can see from any angle you like. This one's actually worth waiting till the end because I used the Daz Animation Studio and you can see what happens when they get to the end of their little routine here. It's a bit...
Oh, I don't even know what's going to happen here.
Well, you will watch and see. Sometimes when you look at these things, they sort of like turn inside out because the translucency of voxels, which is a real thing to do with voxels, is they're translucent, so you get suddenly they appear to be inside out, the way your brain, see, they morph into zombie walks and walk off.
We should probably...
Yeah, so anyway, one last thing I'll talk about here, translucency of voxels. All holographic displays are by very nature translucent. So if you don't want to display, he looks like Homer Simpson there, that's actually his mouth and internal mouth organs. So stuff that you render, or the 3D geometry, you have to start thinking, do I want this to be seen? And if you don't want the geometry to be seen, it's not going to be taken care of by a shader or whatever, you know, it's actually going to be it's there unless you color it black. So that's the Voxiebox. It looks kind of the same as this, but this is a software version of it. So we'll flick back to the presentation there, if we can get it back up again.
Just close there. No, it's not working. Sorry, guys.
That was done using the Microsoft Kinect and iMotion software, I think, to capture. This is a video we did of our real Voxiebox in New York.
It's very loud.
So, this is Tetris. Holographic Tetris. It's really So those last few shots you saw there were the rippling graphics. That was a thing we've got called GraphCalc, which is a math simulator. And it's quite popular. We've showed it to schools, and what that effectively does is render mathematical formulas in volumetric. So people can come in, they can type in formulas, and they see these crazy shapes rippling around, and it's yeah, it's been really interesting. But yeah. We've tried all these different things, and the question was, yeah.
Where do we start?
Where do we start?
And again, this comes back to what industry, where we want to apply it. And the big one is definitely gaming. So if we look at the history of gaming, and especially the social interactions in gaming, it's the way that these sort of things started, like thousands of years ago when people started playing board games. This is an Indian version of Snakes and Ladders. It's about 3,000 years old. And it's just that first example of how people started playing games. And this is a Viking.
It's a Viking board game. Yeah, again.
Again, people gathering around. Actually, he's got a sword. I don't know how to have a camera back then. But, so again, that social interaction around the board, and then moving on.
It's a game of Go. It's a Chinese game. I've heard this is very old, still played a lot today. But again, what we're showing here is social gaming in the way social gaming was played by real people in a real space, and it's that eye-to-eye contact you have with people across an actual gaming space that we thought was really important in social gaming. Here's some psychotic-looking children playing chess. This is a creepy girl in the middle, looks like she's possessed by the devil. And then, so this is like the Middle Ages. Chess is very popular. We fast forward to the early 80s. You might remember this game. Mousetrap,
awesome.
The classic game. Again, very sociable. Look how much fun they're having together. Hungry Hippos. Anyone played this game? I'm sure you remember this one.
Played it last week, actually.
Yeah.
in the future.
Here's a game you might not remember. It's missing a big C at the front there.
Yeah. But then when you, oh, there we go.
Yeah, we fast forward to when gaming moved away from board games and became digital. People started playing video games. In the early days, although I think this is actually a retro-futuristic kind of shot of retro, some of the main table, but well, this is showing you, video games at one point were, in fact, there's one just out there, cocktail cabinet style, still face-to-face, playing games against each other. And if we go further into the future, maybe you might call this the kind of PlayStation generation, you see people are still playing together, but there's been a slight change in the way they're sitting. Rather than sitting facing each other, they're starting to sit on a couch or a sofa, and they're all facing in the same direction, so the eye contact it's not really happening anymore. And fast forward to today, and here's social gaming. Here's someone being sociable, playing social gaming. So we thought, whilst there's obviously a great demand for this type of game, and it's got its place, what we felt with the Voxiebox was it allowed us to start to see social gaming behavior in a kind of different light.
So yeah, we decided we needed to find some game programmers and make some games. So we've started reaching out about 6 months ago once we started having our first development kit available, and this was just straight C, Java, C#, whatever. So no actual game engine integration or anything like that. And over the past, it's been 6 months?
It's been a bit more than that, I think.
More than 6 months. We've got about 150 developers all around.
About 200, I think.
200 all around the world, just who download our SDK. And very recently, 2 months ago, we started working with Gordon.
Before we talk about that,
yeah.
When we started working with these developers, we started doing these roadshows in America. We'd be sending code across to the other guys, and they'd take the Voxiebox out. That's Ken in the middle driving it there, and doing these code jams. And people will be coming in for an evening and to see what they could do with the DLL and a few hours. And so we started creating games. This is the first game that got created at a code jam. It's Pong. It's just a bat and ball game, but it's it's holographic, and the ball bounces around inside. You've got to kind of keep it on that little square that moves around. It's it in red mode there. This is Will. When we took our prototype to the pub.
Adelaide's gathering of really good game developers. I don't think anyone ever says the real name, it's just ARG. Meets at the Goodie second Tuesday of every month, something like that. And we took it out there and we've got a lot of interest there.
This guy is Joseph White. He's a Kiwi. He programmed a game called Voxitron. There's an interesting little side story here. There's a Polygon video about it as well. They did a little documentary, and Joseph created this game, Voxitron, on the PC, but he wanted to run it on a futuristic holographic projector. But when he finished writing the game, he realized there wasn't a holographic projector, so he wrote a volumetric simulator so you could play it on the PC, and that's where Voxitron came from. And we contacted Joseph about a year and a half ago, and invited him. He went to a demo of the Voxiebox in New York, and he fell in love with it. And so he's coded Voxitron to run on the Voxiebox. That's the first version of Voxitron running on the Voxiebox. So you can play it from any angle, and that's still work in progress. So Joseph lives in Tokyo, and he's got a cafe in Tokyo. He runs this little kind of cool little gaming workshop-y type place where people drop in. Okay, so we saw the social nature of Voxiebox, and we just flipped through some games here. We really saw people starting to gather around it and play games, much like you would in 1982 in an amusement arcade. And that's where we decided to go with it. We had people, young people, old people, all gathering around playing with Xbox controllers. We did a roadshow in Los Angeles a few months ago, where we did the world's first 3-dimensional, 4-dimensional hypercube. So this is a holographic hypercube, which displays, it's an animation to do with space-time continuum or something. Anyway, kids loved it. That's Sarah Frucht. She's a mathematician who designed it, and we helped her program it. So we had it rotating, and kids came in. We made maths fun, which I thought would be pretty hard, but the kids loved maths, and they gathered around it, and they wondered, here's some more social images.
We did a demo at Oculus Rift, and that's Palmer Lucky's Farms.
Palmer's Lucky Palms.
Palmer's Lucky Palms.
So if
have a look at the Voxiebox
you like
there.
My Little Pony, so you might see My Little Pony on Rift at some point, a warning there. And then we had this realization.
Yeah, all of our games and all of our content up to this date had been written from scratch in straight C or Java or anything like that. You know, we'd always been interested in integrating it with a proper games development platform, something like Unity. And yeah, so here we are. So we've been working for the last few months with
This guy here,
Gordon Kent Larson. He's a really switched on guy, and he's sort of just taken our DLL and made a very basic alpha level Unity plugin for it. It's not quite ready for release to even the early adopters yet, but it's not far off.
I mean, what we knew in the backs of our mind was you had Unity with 4 million registered users or something like that, and we thought, you've got all these plugins for Unity. You're doing all this great stuff in Unity. You can bring in physics and whatever, and rather than reinvent the wheel and see and have to do it from scratch, wouldn't it be fantastic if people could take their existing Unity games or demos and just run it on the Voxiebox? It would just save a whole world of pain. So that's what we asked Gordon to do. We didn't know how to do it, but we knew that it was an open source .NET framework. You could access DLLs. Would there be a way of getting the data out of Unity and into the Voxiebox in real time? So that's kind of the remit which we set to Gordon. And he came up with this technique. This is using a shader technique on the GPU called depth peeling, where you run through a scene and you get all the geometry after it's been through the lighting pipelines and blah, blah, blah. And you save the data to depth, to color textures. These are just fly through a scene. And then it gets sent to the DLL. So I think this is
We've got this on video.
I'll just skip through here, and you can see a video of our very first Unity, how to create a Voxiebox game in Unity, right? This has only been out for 2 weeks, but hopefully it'll make sense to you. I've used Unity twice so far, and I managed to make a ball appear on the Voxiebox, so I was pretty delighted. So here we go. You open up Unity, you create a scene with a little robot man in it, and you set the scale to, I think it was just like 1 by 1 by 1. And then you create a camera, or use a default camera, and you scale that camera and you turn it so that it's an orthographic camera rather than a perspective camera. And you scale that, and that camera, once you've adjusted the clipping plane, represents the volume that is bound that will appear in the Voxiebox. So you shrink that right down. It's not quite right though, the way we've done it, it's just a working prototype. So that's a little man inside the volume, and you can see down the scene in the bottom there what he looks like. And then you give it some lighting, because what we're doing now is we're using the shaders in Unity to shade geometry that we can then send to the Voxiebox, because before that we can do lighting on the Voxiebox. So now we're using the GPU to do the lighting. And then we drag in this object called Voxiebox camera, and we apply this camera to it, and then we hit play. And then in a second it comes up on the simulator. So that's it. It's done. So what's happening behind the scene there, it's a bit faint just now, but you can see we need to change the resolution, blah, blah, blah. So what's happening there is the GPU in Unity is going away, running all these shaders, and it's slicing up the scene, and it's running through these loops, and it's getting every vertex in that geometry, and it's making a function call in real time to our DLL. And so what we end up is being able to have, you probably all know what this game is here. Default one, I think it is. On the right hand side, when we run it, we can see the game running on the screen. On the left hand side, we can see it running on the Voxiebox in real time. So that's where we're at just now. We've got our first ever
Yep.
script running.
In terms of interaction and stuff like that, I think we've gone over time already, but so we might just fly through these slides about these.
This is some of the stuff we've been using for.
Yeah, for the interaction. This developer kit is amazing. It's only just been released to the early adopters.
We've been using that and doing point cloud stuff for your Princess Leia holograms and stuff. So if you can integrate this stuff into Unity and create point clouds, it'll appear on the Voxiebox. Yeah. We've also mucked around with that for a bit. Yeah. Yeah, and this is why we're here, because we've got all this technology.
He was going, that's awesome.
We didn't put on that. You Google that. Yeah. We need you. That's the first one that came up, and we thought that was cool.
So we're really just starting out in our adventures into Unity. If you want to get involved, if you want to have a crack at porting whatever you've been working on,
we're going to be here next year.
If you can get it done by then, we'd be happy to get it up there on stage there. So not on stage, but in our booth.
So we don't know where we're going with this yet. We're kind of going along where we've got a lot of interest in initially building arcade units to do that kind of barcade scene. New York's very big into that barcade scene. Retro games are coming back in a big way. Public places, you know, just really crazy stuff. And any media, we're just trying to build some media for it to show people what it can do and show people how easy it is. And then, you know, if you send us a script, we'll play it and we'll put it on YouTube, and we'll, if we ever get to the point where we're starting to commercialize it, make an app store and actually license the games and get them into arcades, that's when we'll start, you know, licensing people to develop games. And when thinking about games from a commercial point of view, obviously you have to try and make games that can earn money on an arcade unit, if that's where we go. So you've got to think about that, you know, multiplayer, let's join in, let someone else put a quarter in, let's keep it going, let's make the gameplay ramp up quickly so it gets hard. We don't want someone putting in a quarter in and playing for 4 hours, you know, some sandpit exploration game. But yeah, there's lots of options there, and thanks for listening.
Yeah. Now, we have gone over time, I think, but we're happy to answer any questions just quickly. Yeah.
I noticed on the Voxiebox you had a sort of glass box around it, I'm guessing to protect hands, of course.
Yeah.
Are you potentially considering any touch interaction, so you can touch the glass and move
Absolutely, yeah.
stuff around?
So there's all sorts of interesting ways you can do that, and yeah, at the moment we are focusing on the core technology rather than we are focusing more on the. We are focusing more on the core technology of, you know, actually making the display work. If there's existing interactive devices out there that have got just an SDK that we can manipulate to.
Talk about Leap.
We've used Leap Motion as well as a form of interaction, but getting a touchscreen embedded in it.
I mean, if the fact is that if you can integrate that with Unity and you're running the DLL, you can use whatever you can make work, because you're just passing the graphics commands to the DLL. So you can use whatever you can dream up. You can use your microphone if you like. You know, it doesn't matter.
Yeah.
What's the CPU utilization on that DLL?
Sorry?
What's the CPU utilization?
At the moment, it runs on a Core i7 on a single core. There's no multi. It's not running on. It runs on a quad core desktop PC. We can run it on. I can run it on my laptop, which is a $1,000 Asus with 4 gigabytes of RAM running Windows 7, and it runs fine.
We've actually had a version of our DLL running on the Raspberry Pi as well. So it's.
So if you just have a more complex scene and
Yeah.
more stuff up.
Yeah, I mean, in Unity, the way Gordon's done it at the moment, with the initial, what we didn't mention there actually, the plugin that's been written for Unity is going to be open source. So we're going to put that on a GitHub at some point and allow people to take that and come up with better ways of getting the geometry out of Unity. So for people who are familiar with the graphics pipeline and can think of more interesting or more efficient ways of getting all that 3D geometry and converting it into one of the function calls which we support. So generally you want to get it down to, rather than using, you know, the sphere function caller thing, you want to just use like a triangle or a quad and just or a voxel. And so if you can convert all your geometry in your Unity window, however you want, then you're quite, you know, welcome to suggest or even just, you know, make your own version of the script, because it's not compiled. It's going to be out there. You can see the C# script, isn't it? Yeah.
Yeah.
Oh, I was wondering if you've got any ways of interacting with the stuff. I guess talking more about like typing it, but you use like a mouse or.
Yeah.
Yeah. We've used Space Navigator, Connect, Leap, Intel cameras. Yeah, we've used everything out there. Even Ken was using those. What you call those? Razer Hydra things. We use Xbox controllers.
You just move it around in 3D, like
Yep.
the mouse moves in 3D, not in 2D.
Yeah. I mean, with the 3D mouse thing, the connection, what's that called? Space Navigator is absolutely made for this display, because you can physically lift a model up and down through space, and you can twist it, and you can scale it, and it's very natural. Yeah.
I'm just aware that we have gone over time. Are we stopping someone else from getting up here, or we are? Okay.
Okay. One more question.
King Iron Fine, probably, I don't want to say enough.
Yeah.
All right.
What RPM is the first video?
the latest one isn't using the latest one on the screen is the previous one was a helix. The one that we're using now is going up and down again.
So we started off up and down, and then we went to the helix, and then we moved back to up and down.
Because
didn't really
we
cover
found
that
a better
before.
way of going up and down. That sounds
So
kind of
it's moving
rude.
about 20 hertz, yeah.
20 times a second, which means 40 and it's interlaced. So on the upstroke, it's doing just like a old-fashioned TV. On the upstroke, it's like 190 slices roughly at the moment. So on the upstroke, it does the A slices, and the downstroke it interlaces and does the other ones.
I'll start back up here.
Yep. Yeah, the volume we've got just now, the latest prototype that we built in Adelaide is 15 by 15 by up to 10 centimeters of depth. So a kind of a small like lunchbox sort of size thing, and we're trying to make it bigger and bigger and bigger. One of the issues we've got just now is we're really pushing the boundaries with projection technology that allows us to. We're only currently using fairly low brightness projection systems, where we're working with Texas Instruments and various other companies to make brighter projectors, because as the volume gets bigger, the light output, because you're scaling over in a volume as opposed to on a flat thing, so we need more light. But yeah, to get to what we see as a sweet spot for an arcade unit, the feedback from the big franchises in America like Chuck E. Cheese and various other barcades, they're talking something like 40 centimeters by 40 by about 10 to 15 centimeters deep. So it's another order of magnitude bigger. But we've gone from this size to this size, and we're still working in full-time jobs and have families to do around at the same time. So yeah.
To that point, why did you go down the route of projection rather than like an LCD array?
It comes down to frame rate. You just can't do the frames. There's no current way of getting more than, it's interesting with LCD screens, like you see on TVs, they're all locked out at about 120 hertz because that's what you need for 3D. When you go to OLED technology like that, theoretically, because they're LEDs, they can go at, hundreds of thousands of frames per second, but the actual control circuitry that limits that is actually fabricated into the glass itself in the manufacturing plant. So it would take someone like, Samsung or LG, or someone who actually manufactures the glass to say, we're going to make you a version with the drivers, and then you've got to physically move,
Heavy weight.
probably a heavier weight up and down as well. So yeah, obviously, yeah.
I think we really have to wrap it up
Yeah,
there, guys.
okay.
We'll be hanging around outside anyway, so if you've got more questions, come see us.
All right, thank you.
Thanks, guys.